Okay, we have here today a pretty interesting looking integral from the UNSW Integration Bee 2022. This was knockout round 3, problem 5. We have the integral from 0 to infinity of the sum from the floor of x to infinity of 1 over 2 to the k times k plus 1 dx. Okay, the first thing that occurred to me on this one was, we have a bunch of stuff here and the variable is k, it's not x. So if everything was k, then this would really be just a constant value and we could bring it out front of the integral and just integrate 1. But we can't quite do that because we do have a dependency on x right here with the floor function. But the good thing about the floor function is if it's within an integral of width 1, then the floor function will just reduce our x to a constant value, and then this really will become a constant. So what that's telling me is I need to break this up into integrals with width 1, and so we'll do this with like an integral from 0 to 1, and we'll have one from 1 to 2, and we'll do this, and I'll have to just write all these out all the way to infinity. Okay, so instead of writing this out all the way to infinity, I've written this just 3 integrals so that we can get a feel for it. And what you'll see here is now, and so you notice within these sums, I've just updated this to a constant value now. And the way I did that is like in our first integral, if our bounds are from 0 to 1, and we use the floor on that, so our x value is 0 to 1, the floor is going to take us down to 0 for everything in this region, so that's where I come up with k equals 0. And then with the next one, it's the same idea from 1 to 2. If I take the floor on my x value from 1 to 2, then the floor takes us down to 1, so we have our k starting at 1. And then the same thing here, and it'll go on and on. So what's going to happen now is for each of these, now we really do have just a constant value with no dependency on x. So this is going to be just some number. I'm going to call this one a, we'll call this one b, we'll call this one c, and it'll continue. So in each case, we're just going to have a constant that we can take out of the integral. We'll be integrating 1. We integrate that, we get x. So after we integrate each of these to x, what this is going to look like is something like ax from 0 to 1 plus bx from 1 to 2. And this is going to just keep going all the way to infinity. Like for this first one, we plug in a 1, we have 1, we plug in 0, we have minus 0. And so that width is going to be just 1. Like when we evaluate this one from 1 to 2, we're going to have 2 minus 1. And so what's going to happen is in each of these cases, we're just going to have a 1 here. And so because this width is always 1, we just have this sum of a plus b plus c. So the integration goes away completely, and all we need to do is just sum up all these sums, a, b, c, d, all the way to infinity. What I thought I would do is write out some terms just so we can get a feel for it. So like starting with our first integral, if I just plug a 0 in for k here, 2 to the 0 is 1, 0 plus 1 is 1, so our first term is going to be just 1. And then our second term, when we plug a 1 in here, we get 1 over 2 times 2, and this is our 2 times 2 here. And then when our k value is 2, we just get this term here. When k is 3, on, and this will just keep going on forever. Now when we look at our b sum, it's really the exact same thing. The only difference here is that we're starting our sum at 1. So all we really did is we removed this first term, we removed the 1, but then we have everything else is the same sum. And then for this third integral, we're starting at 2, so we're just missing this first term and this second term, but we have the rest of the sum to infinity. And I stop at d because I don't have enough space, but of course this is going to keep going, and we're just summing up all this stuff. We're summing everything all the way down, all the way out. But of course there's a really simple pattern to this. If we go into this first column at k equals 0, well, we only have one term, just this one right here. And then when we go to the second term, we just have 2 values, just these a and b. And we notice when k equals 2, we just have 3 terms, or k plus 1. And when k equals 3, we have 4 terms, or k plus 1. But the nice thing here is this k plus 1 is this thing that we have here in the denominator already, right? We're summing with k plus 1. So all we need to do with the sum is we're actually just going to use our a value and multiply every term by k plus 1. Okay, so now I've rewritten our sum starting at 0, and just notice that I've multiplied here in the numerator by k plus 1, because that's the multiplier we need on every term to get our full sum for all of these infinite many integrals. But the beauty of that, of course, is now we get cancellation, right? Because we cancel that k plus 1 with this k plus 1. And now we just have 1 over 2k, and what I'm going to do is I'm actually going to write that, let's just write it as 1/2 to the k. But now that we have it in this form, this is just a geometric series, and we have a formula for this, and we should be able to solve this pretty quick. Okay, we have our formula for the geometric series over here on the right, and you'll notice this isn't exactly the right form, right? Our bounds, we're going from 0 to infinity. We have an exponential function here, where instead of our exponent being n, we're using k here. So to match with this form here, we're going to have this will be our r value right here, the ratio that we're multiplying each term. So we're going to say our r value is 1/2. Now we have this condition on geometric series that the absolute value of our R value needs to be less than 1, but of course a half is less than 1, so we're fine here. And what that tells us is that our series is going to converge. Now for our A value, we could just write like a 1 out front here as a coefficient, because there is no coefficient, so we're just going to say our A value is 1. And now we have everything we need just to solve this using our formula over here. So for our A value in the numerator, we're going to have just a 1, and this is going to be 1 minus our R value, which is a half. So then we're going to have just 1 over 1/2. And then if we divide 1 by 1/2, we get our final solution, which is just 2. Okay, pretty cool. So after all that, this thing just reduces to a simple 2. So we'll stop it there. Thanks everyone for watching. Please like and subscribe. Have a good day.